I'm Parker. I work on PJRT at Google, and I'm going to give a quick update on the what we're looking to do for the rest of 2025, and then a kind of deeper dive on extensions, and in particular, a really cool extension that we're working on right now. What is PJRT? Just a quick refresh. PJRT is part of the boundary between frameworks and applications, and the compute devices that they're using to do ML, AI, all of these like high performance compute tasks. Stable HLO is the language abstraction. This is how you describe the task that you want to accomplish. PJRT is like the uniform device API for command control, data movement, etc. So you can see that we have our tile of different applications and frameworks. All of those applications and frameworks are producing stable HLO. Then we take that stable HLO and we use PJRT to interface with a stack of all of our different plugins, whatever hardware backend you might be trying to use. New features and roadmap. So the first couple of slides, there's a few slides in here that are already in the code base today that have been landed over the last couple of weeks. There's also some new stuff that is coming down the pipe. The registration helpers are already there. What we're doing is providing these kind of simple build targets that you can use to create composable applications inside of like PJRT, inside of PJRT land. You can provide a registration helper for either static linking or dynamic linking. The plugin provider gives this macro on the static side that registers a PJRT plugin with the name of the plugin and the function that returns its PJRT API. So then this single CC file and that build target is like the one-stop shop. You add that build dependency into your application, and now you have an application that uses that PJRT plugin. On the dynamic side, we have the plugin provider provide a .so, and then that .so file can be wrapped by the CC file and build target with this register dynamic PJRT plugin macro, which also just creates its own build target. What these are doing is they're going and registering your plugin, the provider of the API, into a global map, which then the consumer side, the top half of the sandwich, the get CAPI client, can use to wrap around that API later. So what does that look like in code? The caller can write this generic like top level client code for PJRT, get CAPI client with options. They can call client compile, client execute, just as they would normally. And then by creating, by using the build targets that the plugin creator provided, they can build different kind of composed applications using their generic application code. So we have the application plus static dep1, plus static dep2, and plus the dynamic dep. We can generate 3 different targets for that application just by swapping out the build depth that we're adding in. Any questions here before I move on?
Sorry, but what is it? Is it another PJRT device?
So these 3 deps would be the static CPU, and dynamic TPU. These would each be one of the registration targets from the previous slide provided by the plugin vendor. And then the build target, these just take they take the form of a Blaze target or a Bazel target. And then you have 3 different application CC binary targets. One of the targets where we're actually using this is where we're providing this PJRT CLI and kind of generic compiler tooling. This generic compiler tooling gives you a CLI into PJRT, so you don't have to go all the way into JAX or all the way into building an application layer in order to actually consume your plugin. You can have your PJRT compiler. The tool name is very much still pending. We were going to call it XLA-CC, but it turns out everyone doesn't use XLA for to implement their plugin. So we will provide this tool. You can either have the static target based off of your based off of the build rules that I mentioned on the previous slide, the registration, or you can have you can just point to a .so with your plugin. It takes your input stable HLO and it outputs a serialized executable for PJRT to consume later in the pipeline. So this is just kind of providing you a unified front end. You provide the stable HLO, we'll give you a binary to run later. Along those same lines, we're also looking at the compile only client. This is also already in the external code base. We introduced the concept of Git CAPI compiler. Today, JAX and our other C++ consumers use Git CAPI client. Git CAPI client requires that most of the functions in the PJRT API are actually implemented. In order to initialize an object of the PJRT client, it performs hardware initialization. It depends on having your actual hardware system connected. The compile-only client requires only 3 of the function pointers in the PJRT API to be implemented. It provides you with a wrapper that implements PJRT compiler that then only uses those 3 endpoints, so you can have a more lightweight client. You don't have to be connected to hardware in order to do your compilation. Compile-only plugins, it kind of makes sense that if you want to be able to produce a client that can do compile-only functionality, we might also want to have a plugin that only exposes compiler functionality. So we're introducing a secondary wrapper for the existing create PJRT API call. This requires that you implement 5 different classes in C++, and then it uses those classes in order to generate the PJRT API for you. For the compile-only plugin, you just have to implement the PJRT compiler class, and then we wrap a version of the PJRT API that only implements the things that are necessary for compile. Everything else is safely stubbed out. And then we advertise via the plugin capabilities that it's a compile-only plugin. The motivation behind this is that we really want to decouple compilation from execution. We want to create this ecosystem where you can run your compiler completely separately from your execution environment. We want to look more like the GCC or Clang. We want to have this CLI tool that allows you to compile your plugin. We want you to be able to produce a plugin that only has compile functionality. And then we want to be able to decouple those 2 workflows so that you don't have to do JIT all the time. Diving a little bit into extensions. So what is a PJRT extension? The CAPI kind of was a one-stop destination for if you wanted to plumb something through from hardware all the way up to your framework. It went into the CAPI. What that ended up, I guess the end result of that was that we have the 120 function pointers that are in the CAPI today, of which an unknown amount are actually mandatory for any given JAX functionality or given client functionality. So we wanted to provide this mechanism to have optional functionality in a PJRT plugin without adding to that core API. So these extensions exist at the top of the CAPI struct. They're just a linked list of kind of additional function pointers that are kind of grouped by the functionality that they provide. So in this example, you say, I have a CAPI extension that has feature ID feature 1, and that feature 1 has just 1 additional function pointer that it's exposing to the consumer of the plugin. So I can get my client. I'll call find extension on that client, and then if it has that extension, then I can do the thing that the extension provided. These can also be obfuscated. So the ID that I'm providing over here, it is currently an enum. We provide an enum that has all of the known extensions today. But it is currently just parsed as an int. So you can provide your own extension if you wanted to provide a diagnostics extension. It won't be plumbed all the way through JAX, but you can produce one plugin that then is a shareable binary that has all of the functionality that you need. We're not going to add specific diagnostic functionality that maybe only a single plugin vendor would use, but you can. It's open for you to kind of chain whatever extensions you'd like to into your plugin. We have a number of current public extensions. We have the most used one, I think, and this has been talked about in a couple of other talks yesterday, is the profiler. The profiler extension provides hooks so that in JAX, JAX can call into the extension for the profiler and use xprof. to like demarcate different events that are happening inside of your plugin. So your plugin provides that the profiler extension, and then we're able to use the hooks to start and stop different events. We use the memory layouts extension. This is actually, we're moving towards having memory layouts extension be the only way that you're providing memory layouts. The existing PJRT layouts is, I guess, being deprecated. And this new like opaque layouts extension will be the new way for interfacing with layouts. We have a raw buffer extension, which is also experimental. This is related to the mutable buffers work that I think was mentioned yesterday. We have essentially 3 different types of extensions that exist. The first is an extension that provides a callback that's then used in compilation or execution. Like I mentioned earlier, the profiling API provides that callback so that the framework or the application can use that callback. We have a second one that allows the framework to mutate state. So like the FFI extension, you have a user data add function, so you can add the state that you want that FFI call to have access to during the execution process. And then we have the third one that is providing some generic utility. For instance, the GPU plugin provides an extension that allows you to compile Triton outside of like the normal compile API for the PJRT API. Profile extension, the plugin provides an extension that then the execute process is using. The extension here, like the example that I gave earlier, is the XProf, connecting XProf through JAX into the PJRT land. We can call into the extension for TPU, for example, implements this, where we're starting profile start and profile stop events that then XProf is able to use to visualize the trace of the application. If the extension is implemented, then we have access to this. And if the extension is not, then there's no impact. It's optional. It's not part of the core API. The FFI extension, where we're allowing the framework to mutate state. The framework is mutating the user data that the FFI function has access to during the execution call. So these are not inputs that these are not like inputs that we're calling into for the graph in general, but they are it's data that's available to the FFI function. And then, like I mentioned earlier, we also have the GPU compiler extension, which is providing this Triton compile call, which is implemented inside of the plugin. We want actually JAX calls this outside of the normal JIT and compile flows. So we want to compile that Triton to assembly and then wrap it in a custom call prior to the actual compile function in the API. What does initializing an extension look like? This is an example from the CPU plugin, the create memory descriptions extension. So this is a struct that follows, we have a PJRT extensions struct, and that is made up of this like extension base, which provides the number of function pointers that are in the struct. It provides the type it is using the enumerated type that I mentioned before. And then it has the next pointer in the linked list to the next extension. This function or this extension here has 2 different function pointers that it provides. It provides the memory descriptions, and it provides the kind of that memory. So this is providing kind of a generic additional functionality for the plugin. And then we can see how it's used here on the right. We've added this create memory descriptions extension. We've added this to the get CPU PJRT API. So that function that returns our PJRT API is also going to call this function that initializes the extension, and then it's going to stick it into that linked list at the beginning of the PJRT API struct. And then we have our API. How do we use it? We provide this utility function that just iterates over all of the extensions that are initialized at the top of the API. We look for the enum, and if the integer the enum matches in that traversal, then we have access to that extension and we can use it.
Okay, so I just want to clarify, these extensions are basically, as a user, we can add, whatever the functions we want to add to the PJRT, and it can be invoked using, this kind of method, right? Like find extension, whatever. Yeah.
Yep, exactly.
Like we also have these, kind of example invitations for all of those
yes.
built-in, extensions.
Yeah, exactly. Yeah, and there's no guarantee that if you implement something that's completely custom, right? There's no guarantee that you can access that functionality through JAX or like through the higher level applications. But it is a great way to say that you have this functionality that you want your plugin distributable to have, and maybe you know how to consume from that in your application, but you don't want to produce two different binary distributables. You could add it to the same API.
Okay.
So yeah, I wanted to spend some time talking about one of our new extensions that we're working on. This one has started to land on the OpenXLA GitHub, the phased compilation extension. First, I guess, what is a phased compiler extension? We currently have a monolithic compile definition in the PJRT API. And we want to enable an optional extension that allows you to have, n different phases that you run as part of your compile and make that accessible to users via this optional extension. So why would we do this? We wanted to enable external caching of the intermediate products of the compile. We wanted to enhance the debugging capabilities as well, so that if you wanted to, debug your compile after phase 2, you now have the intermediate products without having to go and instrument, I guess, inside of the internals of your plugin. Why not build something inside of our plugin? There are a lot of compilers that have, an in-memory cache for those intermediate products that it then leverages throughout the compiler lifecycle. Why did we not want to do that? The answer is that we have multiple different plugins. We don't want to implement it for all of those different plugins separately. We also have multiple users of those plugins, and if we lift the cache outside of the PJRT API, we can have a single shared build cache that allows us to store away those intermediate products. So we can have cross-user caching on top of the PJRT API. The phased compiler extension is kind of a type 3 extension. It is providing some generic utility where the plugin provider provides an implementation of the PJRT phased compiler. We have the PJRT compiler class today, and that PJRT compiler class gets wrapped up into as part of the C API by the kind of bottom half of the sandwich. If you're familiar with the C API wrapper impl, the bottom bread of the sandwich. I'll pause and say, who is familiar with the top half, bottom half sandwich terminology, or should I should probably take a few minutes and explain that. Okay, I'm going to take a few minutes and explain what I mean when I'm talking about top half, bottom half sandwich. So the PJRT core API is a C API with a number of function pointers. Outside of that C API, we also have this wrapper class that uses five different C++ class implementations to generate the C API. So you can implement your plugin at the C++ level and then use those C++ classes to implement the C API with our wrapper, the C API wrapper impl. And then on the other side of the sandwich, we have the same 5 classes all implemented using the C API. So you can implement at the C++ API and you can consume at the C++ API, but the actual transport layer between those two is going over the C API. And the reason that we do that is for the purpose of API compatibility. We wanted to make it really easy to implement in C++, and then we wanted to make it ABI compatible, so we had to use C. So if we needed both C across the ABI layer and C++ for ease of use, then we had to have this sandwich of both sides of the API. So the plugin provides the implementation of one of those classes, the PJRT compiler class. We use the bottom half of the sandwich, the C API wrapper impl, to generate the APIs for the phased compiler, given that new implementation of the class. So what does that extension look like, or what does the new PJRT phased compiler definition look like? The old PJRT compiler had two things that you needed to implement, two different compile endpoints. One which takes an HLO XLA computation, and one that takes stable HLO. We're replacing that in phased compiler with a map that registers a function for each phase of your compile. So you could have a phase for optimizing for sharding. You could have a phase for auto-tuning, that type of thing. We have a register all phases function, which the plugin developer needs to implement. And that register all phases call sticks all of the phases into the map, and as well as the like phase validation functions, which makes sure that the inputs that you're providing are actually valid inputs for the phase that you're calling. Then we define phase compile. Phase compile runs from the start phase that you provide to the end phase that you provide, with all of the inputs that you're providing. So notice that it is inputs here. So you can have phases that go 1 to n. You can have phases that are 1 to 1, and you can have phases that are n to 1. So if you wanted to break up your compilation so that you can parallelize the different phases of your compilation, this gives you the ability to do that as well. You can break it up into like parallelizable segments. Yeah.
What is the, definition or the declaration of the phase? Is that a structure or something like?
Yeah, so the phase is essentially a lambda function.
Oh, lambda.
It has a given, the function prototype is essentially a vector of serialized programs. And you take in that vector of serialized programs and you output a vector of serialized programs. So you could pass in 1, you could pass in n, and you can output 1, and you can output n different partial programs.
Wait. It is a little bit confusing to me because from what I'm understanding, basically, like we can, break down a whole pipeline into multiple small pipelines,
Mhm.
and then each phase just represents a kind of a prototype, or like another way, or some representation of probably like some IR in one level. So let's say in MIR, maybe we just start from stable HL and then we lower to lineage.
Mhm.
So like stable HL is one phase, lineage is another phase,
Mhm.
right? So the phase is basically some lambda function that represents like stable HL or lineage, right?
Yeah, it would be the conversion, or it could be the conversion between the two.
Oh, the conversion.
Yeah.
It's basically kind of like a function pointer to some a conversion pipeline, right?
Yeah, so you can kind of think of this. We don't want it to be at the granularity of passes in MLIR, but you can think of this as registering three different sections of your compilation, and the sections of your compilation can also be parallelizable. So if you have one that does all of the sharding for your graph, for example, and that produces 4 output shards, you could take and run in parallel each of those 4 output shards, and then you can have a phase that consumes those 4 to generate your final executable.
At the interface level, it's like super open-ended, right?
It is
like,
very
that's
open-ended.
How you want to use it.
Yeah.
But like in theory, you could put like MLIR phases
Anything.
in there.
Yeah.
Great.
Yeah.
Cool.
Like we're gonna primarily consume this internally at Google for like our own build tooling, I think. But yeah, it could be useful to other use cases too.
Comment and a question.
Yeah.
Question first. So this sounds like a powerful interface, very open-ended.
Yeah.
Interface. Are you defining or expecting the provider to define the serialization format that's going to be used?
Oh yeah, great question. So we are defining the serialization format as it must be serializable to bytes, and we're leaving it very open-ended. From that perspective, we are wrapping your bytes with a proto structure that has 3 fields that indicate the phase that it came from, the version of that particular compiler you were working with, And I think there's a third one that I can't recall off the top of my head. But we will provide kind of a wrapper proto around your serialized format. There are some fields that we want to be readily accessible to the client when it looks at that file for the first time, so that we don't, for instance, pass completely invalid bytes across the interface to the plugin.
I don't know how to handle the caching part of this. We need to be careful because multiple compilations might use different flags, for example, in the compiler.
Yes,
right?
exactly.
Intermediate forms they generated using one set of flags, and then you're passing a new set of flags.
Exactly.
Okay, that's my question. My comment is, I found that being one of the lower end hardware providers of a compiler, you ultimately get down to calling CUDA or GPUs. People are very confused by, there's an XLA compiler, there's a PJRT compiler, there's the hardware system provider compiler, right? And there might be some other compilation, serialization, caching process. And so when an error occurs in a compiler, it's frequently something outside of the space that you control. So how to communicate this in a way, I understand from the compiler perspective, it's a compiler. But this is just a general question. Everybody has their view of the stack, and they're compiling their piece of it, and they're calling it a compiler.
Sure.
But we're a very deep stack of software that we're offering customers, right? And it's very confusing to them to know what the compiler error is, because it's the different layers of the compiler.
Sure.
We should be industry-wise smarter at naming things.
Yes.
So we can make it easier for users to understand. That's a comment, not a question.
Yeah. Agreed.
PJRT is actually not a compiler, I would say.
It's space compilation.
It has it's true.
It is an interface around the compiler.
It's an interface.
I understand.
Yeah. No, you're right. It literally says it on the slide.
It does.
Yeah. And errors can come from the PJRT compiler call.
Which then gets sent to me saying, because the compiler failed. It's like, not my compiler.
Yeah, right. We struggle with this too.
What does this look like at the CAPI? So the extension needs to wrap the functionality that exists in this compiler. So we have a couple of different functions that this compiler has. It has an endpoint that returns a list of all of the phases that exist, all of the phases that you implemented and registered. So that's get phases. And then we have the function pointer for run phases. This takes, again, like I said, the start phase, end phase, and all of the inputs that you would typically pass to the compile. That input is, like you mentioned, the cache key. So that input will have all of the flags for the entire run. So you have to have access to that full set of flags. You can't provide different flags to one phase of the compile. And then we have the get phase compiler, which initializes that phase compiler object and returns you a handle over the CAPI that you can use to interface with it later. And then destroy phase compiler to clean it up later. And then all of this is wrapped around this implementation. So like I mentioned, you have the bottom half of the sandwich that wraps that C++ implementation layer in this nice kind of clean CAPI. You don't have to implement directly at the CAPI. You can implement directly at the CAPI if you want to. You just implement directly these function pointers. And I think that's all I had on the phase compiler. So I will open it up for questions. I have a couple of conversation topics that we could talk about. Who implements directly at the CAPI?
The PJRT CAPI?
Yeah, the PJRT CAPI. Okay. I guess who are hardware vendors?
Yeah.
He had a PJRT plugin in the works.
Yeah, like
Talking
I mean, he copied from TestStorm.
Well,
I just use it, and I don't know how it was implemented.
It makes, does anyone here implement like the C++ API and then use the C to C++ wrapper? I think probably most people
That
here
I
are
don't
not.
know.
Okay, gotcha.
I didn't write it myself. I'm using it right now for bring up on our torch path, but it's been written previously by someone else.
Yeah,
We're still working on it for our JAX path
Okay.
specifically, but we're going to use OpenXLA and that in tandem, I guess, right?
Oh, so you have it working on TorchXLA and you're reporting to JAX?
No, other way around.
Other way
We have PJRT API. I mean, it's not like fully implemented with every single
Yeah, sure.
endpoint implemented, right? But we have it like a JAX front end with front end. I mean, it's just a
It works with JAX.
implementation. Yeah.
Yeah,
Yeah.
same.
And then you also want to work with TorchXLA.
Yeah.
Yeah, I mean, it's the same. Like, like our team also have that supported, but we want to work with Torch XLA, which has a lot of troubles.
Yeah, that's sad. It's not what it said in the diagram.
Awesome. And then I think everybody in the room is semiconductor or hardware vendor, right? Is there anyone that does not produce a plugin? Oh, okay. Do you consume at the CAPI, or what's your connection to PJRT?
I've seen PJRT in many back traces, and I wanted to learn.
Okay. Awesome. Very cool.
Yeah, we could briefly go over the stack.
We could.
We can only do the JAX stack, or unless you know the Torch XLA stack.
I don't know the Torch XLA stack.
I was just saying,
I don't know it in detail.
info session, so this will bridge the gap. I got that first part over there.
Yeah. But but do you guys know anyone who who knows the Torch XLA stack using PJRT?
Oh,
I just want to know the name and what email address we can probably talk to them
well,
later.
no, but who?
So I guess I can go over what I do know about the PyTorch XLA stack. So JAX and PyTorch XLA both use the top half of the sandwich that I was mentioning earlier. They have this magical thing called the Git CAPI.
As you speak.
Yeah, okay. We have this Git CAPI client call, which wraps the CAPI. Actually, I have a Lucid chart for this.
Oh, great. Yeah.
So this is kind of the overview of the stack for PJRT. We have the C++ implementation helpers, which is what I was talking about earlier. And then we have the CAPI wrapper. This is the bottom half of the sandwich. So we have this wrapper implementation that takes all of these class structures in C++. You can implement directly at C++. And then it wraps all of those C++ structs into this CAPI function pointer struct with all of the 120 different APIs that you can have in the CAPI for PJRT. So I have this on the screen. This is a dotted line. This is a dotted line because this is technically the only thing that you have to implement. You only have to implement at the CAPI. This is a convenience. We recommend that you use this. We put a lot of nice safeguards in here, and it's cleaner and easier to work with. And then on the other side, we have this other thing that's cleaner and easier to work with. That is the PJRT CAPI client. PJRT CAPI client implements PJRT client using the CAPI function pointers. So you don't have to go directly and form all of the C args structs and manage the life cycle of all of those kind of C handle objects. You can just create that instantiation of the class and then work with the PJRT API. I mentioned earlier we have the registration mechanism. The registration mechanisms are storing pointers essentially to the different instances of the PJRT API. And then we have this PJRT CAPI client thing that takes different platform identifiers to create the wrapper. We also have, all the way on the left side, we have even higher level helpers with which instantiate plugins for individual named platforms. So internally, we have TPU, CPU, and then GPU. These are the three C++ higher level helpers. So on the left here, this is the top level of the sandwich. It's a sandwich and not a thick client. Why do I use the term sandwich? Because it is the same bread on both sides of the sandwich. We have C++ class bread here, and we have C++ class bread over on this side of the sandwich. We're implementing the same interfaces. So at the end of the day, you can implement and then call at the same C++ layer. C++ makes it really easy to use. So why do we have a C barrier at all? We have a C barrier because C is how we get ABI compatibility. And that's what gives us the ability to have like backwards and forwards compatibility guarantees around the plugin. So I was talking about PyTorch. How do PyTorch and JAX interface? with the top half of the sandwich. So both PyTorch XLA and JAX are calling this function, the C. I put my hand directly in front of that. They are both calling the PJRT CAPI client constructor to get the wrapper around the CAPI. So PyTorch XLA creates that CAPI client and then interfaces directly with that CAPI client. So it's producing a graph, it's calling compile, it's using the execute functions directly. JAX does not. So JAX has a higher level wrapper, which is, I think, not in any of the 10 slides of this PJRT overview Lucid chart. But yeah.
I'll just send you a screenshot.
Okay. So we have the IFRT wrapper, which wraps PJRT. And then IFRT is kind of a higher level multi-device, multi-host view of PJRT. So you have IFRT implementation that is just a pass-through. It says there's only one PJRT instance. I only need to pass through my commands to that single PJRT client. But then there are also implementations of IFRT that create a multi-host like representation. So there's 10 different PJRT clients and you're managing the different collectives across those different instantiations of the client. JAX does that. PyTorch XLA does not. PyTorch XLA is expecting single PJRT client.
You only get the multiple PJRT clients with like pathways.
Yep, pathways. Yeah.
Like
one question.
Yeah.
Wondering, is that intended to implement heterogeneous computing, like using different devices?
Oh, that's a great question.
No.
Yeah.
I don't think. Actually, no, that's not true. We have like host offloading.
Yeah. So host offloading.
That's the only type of heterogeneous compute we have.
Host offloading currently does not use two different PJRT plugins. It's just CPU and TPU baked into one plugin. I think there is a goal to have host offloading be loading two plugins and communicating between the two, but I think that's the only example.
To be fair, is this really a question for PJRT? I think that you probably need more like end-to-end.
Yeah, I mean, so yeah, and host offloading that happens like kind of like underneath even PJRT. It's like the compiler deals with that.
Yeah.
Yeah, the point of IFRT, here, I am going to draw the picture. So it's like, just so, like, yeah, you have like the PJRT C API, and so yeah, this is like sort of like the official, like this is the boundary between like frameworks and like hardware vendor plugins, including like, you know, Google TPU or whatever. And then, yeah, and then so then you have like the sandwich, and so this lets us use like PJRT, like C++ to C, and then like in the other direction we also have like C to C++, and so like I should use different colors. Green will be an interface, and so then like here we're like back into PJRT, like C++ on both sides of the sandwich. So the whole point of the sandwich was just a trick because like we originally just had like direct statically linked C++ code and we wanted to like pluginize it. So we like inserted the C API and we did it simply. Okay. And then so on top, I guess this is actually also as an interface, you have IFRT, and so everything is C++ unless it's PJRT C API. So like this is for basically, it's like supposed to sort of be like a multi-host runtime.
And the reason why it's multi-host is like it has concepts of like which devices are addressable by which clients and which clients need cross-device communication in order to share data, that type of thing.
Yeah. But even PJRT is like single host like ish.
Yeah. Yeah, so like for TPU, for example, you have, if you create a single client of PJRT for TPU, and you look in the devices, and you look and see like what does devices return for PJRT client for TPU, you end up with a set of 4 devices, some number of devices that is not one.
It's like there's like so a leaky abstraction between the multi-host here because PJRT, like this is where we plug in like different actual hardware types. So you know you have like AMD, like Google, and okay, sorry for everyone to mention. And then like and CPU and different types of GPUs and like whatever. Okay, and then like yeah, so it's like some of the multi-host like topology information, like what makes sense in a multi-host config for like Trainium. It's like that has to go in PJRT because that's like the only like IFRT is actually platform agnostic. And then so yeah, the main point of IFRT is that like either you have kind of like the default JAX way, like the open source multi-controller JAX is like a very straight pass through to PJRT. So it's like IFRT is not doing much heavy lifting at all. But then also is where we plug in pathways. So like IFRT is basically like a pathways interface. Like it's how JAX like switches between pathways and not pathways without having to like we want a common interface to abstract over that switch. And then so what Parker's saying is that on top of that you have this JAX calls IFRT, but PyTorch XLA goes straight into PJRT C++. So that's a picture. Sorry, that took longer than I thought.
That's perfect.
Yeah. Okay, so I just want to clarify. So each device or like each type of device is going to have a a PJRT client, right? So let's say if my system has one CPU plus a bunch of let's say TPU, then we might need two PJRT client to manage this kind of system. Or
it depends on how the plugins for those. If you go and implement a plugin for your system directly, and you say that my system is always going to have one node of CPU plus 8 GPU nodes, and that's how you've architected your system. You can write a plugin that is a single PJRT client, which knows how to compile for one CPU plus 4 or 8 GPU nodes, or etc. Right? You could also say, oh, I know that I have XLA CPU today, and I know that I have XLA GPU today, and you could go and create one XLA CPU client, and you could have 8 XLA GPU clients.
Yeah, but like that can only work with JAX, right? So if you
that actually would not even work with IFRT.
What I will say is that like PJRT, like this interface really is designed for like one accelerator type. But in theory, the interface, like because it's very high level, like you could have different device types in your plugin, but it's like the device interface doesn't have like a type.
Yeah,
concept.
exactly.
Like it might be hard for users to effectively use, like if you're like we just didn't have that. And then like kind of back to your question, we actually like we also don't have good like you can imagine having like your CPU and your like AMD GPU plugins, but like we don't have good there's not interfaces for like plugins to really work together in that way. It like basically everything has to like bounce through the host to go to different plugins. But so if that is something you need, we would need to think about the requirements. It's just like, our accelerators don't really look like that, thank God. And then if we are doing host offloading, we just like do that like outside, like totally within this abstraction. Like you'll just compile a program that's like actually the thing that gets executed like inside this box.
Yeah, you can put inside of
host stuff.
Inside of that box, you could have your 1 CPU by 8 GPU topology,
so this
right?
Might be like, huge.
But if you have one PJRT client that is wrapping your CPU and 8 PJRT clients that wrap your other 8 GPUs, we don't have like a wrapper implementation that implements all of those collectives for you. That's not something that exists in JAX or IFRT. Does that make sense? Not to say that you couldn't do that, but it would have to go through the host in some way.
What I'm trying to illustrate here is that like you call execute on the PJRT interface, and it's like now we're in like magic whatever land. Like
something happens inside of the plugin.
Yeah, like we don't care now what you do. And that could include host offloading.
Oh, okay. So
so who's responsible for deciding which parts of the program to put on which machines with which TPUs, for example, like in a many machine, many TPU configuration? Does that, let's say, I guess it's probably a different for each thing, but
for TPU, like I mean that's you can define it with Shardy, right? For like npmd and spmd.
I mean, like, so who's responsible? It's like in practice the user.
the user decides how to.
Or no, it depends. Like actually, okay, so JAX is like different APIs, right? Like, and this is where like Shardy and like JSPMD, it's like JAX's JIT API can leave things very open-ended. And then so it is ultimately the compiler's responsibility to decide that.
Like XLA.
Excellent.
So even if you have a
compilers, right?
Or it's like, okay, from the PJRT perspective, here, let's like also briefly go over like what PJRT looks like. So it's like what PJRT, it's like a very high level and we're trying to be generic API. So like the main functions of PJRT are compile. This is not necessarily XLA. Although JAX does and PTXLA will give compile stable HLO basically. Like PJRT doesn't even mandate that it's stable HLO. But in practice it is stable HLO, right? It's like that's what these frameworks are gonna stuff through PJRT. But PJRT in theory could support even other, like any program definition. It's just bytes to PJRT's perspective. So yeah. So this is like bytes, but like it's actually stable HLO. And then compile gives you an executable. And so then there's like execute, the executable, and also some like buffers as input, like in buffs, and this returns like output buffers. And then the last thing that PJRT, there's two things. It also does transfers. So this is like hosted device to host, DDD, like where do these buffers, like managing these buffers, deleting them, transfers, or in general, just like memory management. And then like the last like weird thing, let's start because it's weird, is like PJRT also actually handles like the topology information. And this is where, this is the ish, where it's like, it should just be these straight runtime things, but because this is like our platform interface, it's like we also need to get information about like what size slice are you on, like how many devices are there, how are they wired.
Like the TPU topology will have both addressable and non-addressable devices in the PJRT client.
So from like
because XLA needs all of that.
Yeah, like so PJRT is very generic. It's like in theory you could stuff anything through this, but like in practice, yeah, like JAX and PyTorch XLA have like different APIs that like the thing that goes into this compile call will like have different information about like, oh, actually I want to run on these devices, or actually like compiler, you take the wheel and you choose. And that's sort of like a whole other contract. So that contract in practice just looks like what XLA gives you. Because that's what like JAX and PyTorch XLA know. We don't know about other compilers. Does that answer your question?
I think so. So then
like there's a concrete answer for like exactly how device placement works. And it depends which API you're using.
Right. But there's like some API that gives all of the device information to XLA. And then XLA can sometimes call back to PJRT for transfers or something.
So it's like XLA is inside PJRT. It's like in practice, each of these boxes like has XLA inside of it.
But
or something
I think
that looks like XLA.
For maybe like if you pass the 4 devices here that one PJRT client is connected to, and then that PJRT client is also, because you want to run with 8. Let's say you want to run with 8 TPUs. Your PJRT client knows about these 4 and can address these 4, but those 4 are actually connected, however they're connected maybe. And then your topology has to include both the addressable and the non-addressable devices. And when they're connected like this, XLA has to know about all of them in order to manage the interconnects between those devices. In that case, XLA is handling it. But the second that you get to IFRT and you have this device and like an RDMA connection to like these devices over here. XLA doesn't know how to do this.
Actually, doesn't know how to do it. But you'd have to like do it through a compile and execute call.
Yeah.
Yeah. So that's one way to do
So
it.
they can call each other.
They can't call each other. It's like the calling definitely goes one way, but it's like yeah, like okay.
This collective is handled differently than this collective. This collective happens differently, and typically like up here. This happens typically down here.
Yeah, it's like XLA actually. This is confusing. XLA like or whatever compiler like this execute call has its own runtime. Like that's this cloud, right? Like you're executing something here, and like the plugin knows how to do that. But it's like, so PJRT, and like this execute might include communication, right? Like this is a multi-device executable. Like it's going to do communication. It has to know how to do that. It doesn't call back into PJRT and knows how to do it itself.
Gotcha.
So like there is overlap. PJRT is like a higher level thing, and like it also has these like memory management APIs that might overlap with like.
But like also the same thing down here that we were talking about with like the one CPU and like your 8 GPUs. Like if you built a plugin that was that topology, then your plugin needs to know how to execute with the communication for all of those devices, right? Like if you have two devices that you know are connected over like some Aurora interconnect, right? Then you know how to talk over those two devices.
Yeah. So okay, yes. So I also just want to clarify. So when you were saying like one plugin and like so basically like one plugin basically have to implement all of the all of the compile, execute, and also the topology in the red blocks, right? Like it just like in one red blocks.
Right in the red blocks are devices.
Yeah, like like kind of something like
whatever you want to wrap and say like is your compute unit.
Yeah, so
it needs to know how to handle that.
Yeah, so the compile call is like this is sort of like how XLA works. Is like this actually has like the full like input to it is like
and a topology.
Yeah, the full global.
The topology. Full thing, yeah.
And then so it's like when there is like a contract, there's an implicit contract between PJRT and execute. It's like PJRT will make sure that every single device is executing. Sorry, only on one host, but then like PJRT running on all the hosts. Like it will make sure that you're
because you have another
this on all the devices, but it's like the program itself does know like, oh, I am part of this like larger execution.
Oh, great.
So
yeah.
like I'm gonna do a DMA to my neighbor.
Yeah.
And like hopefully the neighbor's like, I'm expecting a DMA from you. Yeah.
Yeah, it makes sense. And also like so what if let's say just back to the previous example, I have one CPU and let's say 8 TPUs, and then like I just wrap it within one PJRT plugin. And then in the front end, like so just let's say when user calls like xm.get devices, what is going to get? Like is that just a topology with like just 8 TPUs with one?
It would call the plugin. It would call the plugin's implementation of get devices, and then
and then just directly. Great.
Yeah, so that's like this funny one. Like the plugin also gives you like this is like devices.
Yeah. I see. Yeah, it makes sense.
Awesome. Well, thanks everybody for coming.
Yeah, thank you.
Yeah,